Okay, hello everyone. I'm guessing this is going on. Okay, so I'm going to be covering mainly the pre-midterm material, but effectively what we've decided to do is between me and Fawaz, I'm going to be covering what is basically the non-medicine half of the course, while he's going to cover the medicine half of the course tomorrow. So I'm going to be reviewing a lot of the pre-midterm stuff, and then he's going to be reviewing the clinical applications tomorrow, and at the end we'll be doing questions together. Feel free to stop me at any time for questions or type them into the chat and I'll try to go through them as we go along. Okay. So there's the objectives. Now the basic principle of medical imaging, just as a quick introduction, is that, like as the name suggests, we are taking pictures within medicine. So we want to visualize the body, we want to see how it's running, want to see how it's functioning, we want to look at the structure. But it's pretty inconvenient to have to take the patient to the surgical room every single time we want to look at them, so we use medical imaging. So, first of all, we have a quick history of radiology. These are numbers you need to remember, and the name Wilhelm Conrad Röntgen, or Röntgen, I don't know how you pronounce that. Interestingly enough, both of these dates are wrong, but I'm not going to rag on to them too long. This one's supposed to be 1895, and this one's 1901. But whatever. So then we moved on and we started using chest x-rays to screen for TB. Again, it's just another date, so I have to memorize. And finally, with World War II and the destruction of the Empire of the Rising Sun by the sun itself, we discovered nuclear fission, and then we started using nuclear medicine as well. And yeah, so in August 6th of 1945, we had the nuclear bombings of Hiroshima and Nagasaki, and that opened up the whole field of nuclear medicine as well. This is just the basic principle behind X-rays. So you have an X-ray tube, which is the source of the rays. What you're going to do is you're going to shine a bunch of beams of X-ray light. They are going to pass through a subject, which is your patient, and then finally they're going to hit an image or a screen on the other side. This is just what an X-ray tube looks like. So here you're going to have a cathode. I don't know if you can see my cursor, but assuming you can. So there's going to be a cathode and an anode. The cathode is going to shoot electrons at the anode, and the basic premise behind it is that these electrons are going to have a lot of energy. So when they hit the anode, they're going to lose some of that energy. They're going to slow down, or they're going to hit some of the atoms inside the anode, and they're going to release that energy as light. And in this case, that light is going to be X-rays. And here's a diagram showing that. You have your cathode and your anode. So electrons are going to be flung out of the cathode due to electrical current. They're going to hit the anode, and then because they're hitting the anode and they're losing energy, that energy will be lost as heat and as radiation in the form of X-rays. Okay. Here you have water being used to cool down the anode so it doesn't overheat and melt. This is just to show you the electromagnetic spectrum. Our focus here is X-rays, but with a lot of metals, you'll see radiation get released from a variety of different spectra. But for X-ray imaging, what we care about is the X-ray itself. Here's just a review of the X-ray tube. Now you have your KVP, which is the energy of each electron, or it's the voltage across the wire, like across the X-ray tube. Right, so if you think of, for example, a battery having 3 volts, that's going to be your KVP. Meanwhile, your MA, that's your current. And so current literally describes how many electrons are passing through the system per second. Okay, now I mentioned that you're going to have X-rays getting released because your electrons are crashing into the anode and they're losing energy. But this kind of sounds weird because what the heck do electrons crashing into things have anything to do with light? Well, simply put, it goes back to the principle, to the like a very basic principle within science, which is that you can't create energy and you can't destroy energy. And so at any one time, you will convert energy from one form into another. And so if you have an electron and it's passing through an atom, and then it's slowing down for any reason, all of that energy has to go somewhere. And in this case, the way what it's going to go into is it's going to travel into X-rays. And there's several different ways this happens, but the two main ones that they want you to focus on are the Bremner-Strahlung effect and the photoelectric effect. Okay, so with the Bremner-Strahlung effect, what you have, I am pronouncing every single word in this thing wrong, but forgive me, this is not an English course. So with the Bremner-Strahlung effect, what you have is you have an electron, it's going to go to an atom, and then because of the nucleus, like because the nucleus being very positive and the electron being negative, there's going to be some deflection. Right, so you can see the negative electron is curving around the positive nucleus. And that curving is going to result in the electron slowing down. And as it's slowing down, it's going to release the energy from its speed as X-rays. Now, as you might expect, because the deflection can happen in a lot of directions, because the deflection can happen all over the place, this means that this effect is very general, right? You can get all sorts of different radiations with it, you can get all sorts of different energies of radiations with it, but you're going to get a lot of radiation. Now, the second way is the photoelectric effect. The photoelectric effect is where you'll have an electron actually enter into the atom and get incorporated into its shells, into its electron shells. So if you remember from like a long time ago in high school, you'd have these shells around the nucleus where the electrons are set. And so what the electron will do is it's going to slot itself into one of the shells, and as it does that, it will lose a lot of energy because it's slowing down a lot. It will lose a lot of energy as X-rays. Now, because of this, because of the nature of these shells, and because of the fact that these shells are always the same for any atom of the same element, that means you're always going to get the same rays being emitted. Okay, so anytime you're using the key idea is anytime the photoelectric effect is happening, you're going to get the same beam, the same frequency of light. Okay, and it's going to have the same energy. And so this is what that looks like. Here you'll see that there's a lot of different frequencies of light. There's a lot of different energies of light because of the Bremner-Strahlung effect, where they're being deflected in all sorts of different directions, and each time you're going to get a different type of energy. But you'll notice that there's these little spikes here where there's a lot of energy being released, and that's because of the photoelectric effect. Okay? Now there's also another concept, which is the Heel effect. All I'm going to say is that this slide is quite blatantly wrong. And so I'm just going to pause for a second so I can set up and try to explain this. Okay, so what we're going to have is we are going to have the X-ray tube that's over here. Okay, so just draw that. So we are going to have the X-ray tube. Now the X-ray tube is going to be at an angle. Okay, and here's just the cathode, completion, and here's the anode. Okay, so what you're going to do is you're going to have these electrons that are traveling through. Now the key thing is that your detector is going to be over here, right? So anytime these X-rays, let's have those in red, anytime these X-rays want to travel, they're going to have to travel through in this direction, okay? So the key idea is that you see that because they're going to travel from everywhere within the anode, is that the X-rays that start over here have a lot less material to travel through, okay, before they leave and they reach the detector, okay? But the ones over here, they're going to have a lot of material from the anode itself that they're going to have to travel through before they leave and they can go to the detector. All right. And so what that means is that the X-rays that are over here, that are like in this region, let's just change the color again, is that the X-rays that are in this region are going to have a lot less energy because they're going to be very heavily absorbed before they leave. Whereas the ones in this region, let's color that green, whereas the ones in this region are going to be a lot more varied. They're going to have a lot of low energy rays because there's a lot less material for them to pass through. All right, so let's just go back to the slides. Now you'll see here that effectively what's happened is the graph is in reverse, right? This should be, wait, no. Yeah, so this should be a lot of high energy radiation. Okay, so there should be a lot of high energy radiation. No, wait. Okay, so I had things a little bit, I flipped things around a bit. Let's go back. All right. So cathode, anode. It's at an angle. That's okay, it can be green. And then you have your detector. Now the ones over here are going to have a lot less material to pass through, like we said. What that means is they're going to be very high energy when they leave, right? Whereas the ones over here have a lot more material to pass through, so they'll lose a lot of energy. Okay? And so what that means is that the ones leaving this area are going to be very low energy, whereas the ones leaving this area are going to be very high energy. So as you can see from here, the graph is basically flipped. This one is a very high energy ray because it's not passing through anything, whereas this one's a very low energy ray because it's passing through all of the anode before it gets to leave. Okay? And this is why I explained before, where you have your general radiation being very varied, because like we said, the deflection can be in any direction, while the characteristic rays are going to be very specific, and they're going to appear as these spikes. Okay. So once you have your X-rays have left the anode, different things can happen to them as they travel through the body. Right? Just like visible light, they can be absorbed and they can be reflected. All right. And so here's a different concept that is over here, which is basically when we want to release radiation into the patient's body, we don't want all of this extra radiation to be everywhere because that's going to cause a lot of noise. And so basically what we'll do is we'll focus the rays into one specific point, which is the point that we're going to focus on, which is the point that we're going to be looking at in the patient body, and that creates a lot less noise. And the way we do that is through a lot of through refraction and reflection. The main idea is that the X-rays will be focused here, and so this is what you want to be looking at, and you lose a lot of the noise that's going on from the rest of the body. So here we have the X-ray spectrum, and here we're going to be looking at filters. Now, filters are things you'll attach onto the X-ray because you want to focus the beam of light onto a specific spot. And so in this case, so this image here, what it demonstrates is how so this image here is demonstrate what will happen to the X-rays as they'll pass through the filter. Now, for these lower energy rays, they're going to get through the filter, and because they don't have a lot of energy, they're going to be absorbed by the filter. Whereas for these high energy rays, right, they already have a lot of energy, so they have no issue passing through the filter. And in this diagram, okay, so this is a little bit, so putting the graph here is a little bit confusing. So what we're going to do is ignore the graph. We're just going to pretend that it's a singular light source, like a singular X-ray source. Okay, so you have these different X-rays that are traveling through. Okay, and then you have here the patient. Okay, now let's say we want to look at the patient's heart, which is over here. You don't want the X-rays to be going up to the patient's neck, which will be up here, or the patient's abdomen, which is down here. Okay, so what you'll do is you'll focus the filter by using the bow tie shape onto the patient's chest. So what it's going to do is that you can get a lot of X-rays that will pass through this area because the filter is a lot thinner, whereas these areas are thick, so they'll block a lot more of the X-rays. And here's basically showing you what happens, how the image looks like after it passes through the object. So here, for example, there's a lot of dense material. This could be bone, for example. So you're going to get very little X-rays. Whilst over here, there's very little material for the X-rays to pass through, so you'll get a lot of X-rays that reach the screen. And so that's why you end up with a bone appearing as white, because it's blocking most of the rays that come off of it, while, for example, soft tissue and air will appear more as black. Okay. Can I repeat? Could you specify which part you want me to repeat? If that's okay. The one before the slide. Okay, so the collimation. All right, so here you have, for example, the patient's body. Now you'll notice that we only want to look at this part of the patient's body. Okay. Now I don't need the X-rays to pass through all of this. I don't need them to be going all over the place because that's just going to create a lot of noise on my image. All right. So what instead we're going to do is we're going to focus our X-rays so that they go through as minimal amount of the patient as possible. So they go through basically only the part that we're trying to look at instead of going through everywhere else. All right. And so you'll basically reflect the rays using mirrors, and you'll do a bunch of fancy stuff. But the main idea is that you're going to be focusing the X-rays on one part of the patient. So if you're looking at the chest, you're going to focus the beams, so you're only looking at the chest. Does that make sense? All right, so here's what happens with the X-rays as they interact with different material. You have your Compton scatter and you have your photoelectric effect, which is the two main ones. You also have elastic recoil and pair production, but those really aren't as important. All right, so your first thing is your Compton scatter. Now, the key thing with a Compton scatter is that your light rays, so your X-rays, they're going to interact with electrons. Now here, okay, so for this diagram, let's just skip over. All right, so for here we have, let's say, a beam of light, and here is an electron, right? So the electron is free in this situation. So unlike in this image where the electron is bound to an atom, in this situation the electron's just floating around and it's not bound to any nucleus. And so what's going to happen is you're going to okay, so what's going to happen is that you're going to have, why is this lagging? It's okay, I'll just discredit it, it's fine. It's fine. Alright, so here you're going to have an X-ray beam, and you're going to have an electron that's freely moving around. Okay? Now what's going to happen is that this X-ray is going to hit the electron, and the electron will absorb that energy, and it will travel faster. Now later on, that electron will lose that energy, okay? And it will release the X-ray. The key thing is that once the electron loses the energy, the energy that it releases is going to be less than the energy absorbed. Okay? And that's why you get like E1, which is the energy of the X-ray that hits, is going to be stronger than E2, which is the X-ray that leaves. All right? Now, by comparison, you have your photoelectric effect, okay? Which is, in this case, it's interacting with material that's inside of the patient's body. All right? So what's going to happen is the electron's going to hit, the X-ray is going to hit the electron that's inside of the atom, and it's going to eject that electron. Now, as you can see here, the electron's ejected. It's left the atom completely. Later on, this electron will return to a different atom, and it will bind to that atom, releasing X-rays. All right? And so in this case, that's a different way that energy can be absorbed. Now, finally, there's elastic scatter, where all that happens is that you get an X-ray that binds to an electron, right? And because the energy of the photon is smaller than the energy of the electron, so in this case, because the X-ray has a lot of energy, the electron gains a lot of energy so it can leave the atom. In this case, it doesn't gain all that much energy, and so it can't leave. And so all that's going to happen is it's going to gain the X-ray energy, and then it will just lose it again, almost immediately after. And that's why you get an elastic scatter, where this ray and this ray have the same amount of energy. Now here we have the X-ray formation process, where you're going to have stuff like bone, supporting soft tissue, fluids, and air. And you're going to get all of these different rays that are passing through them. And in each case, the way the image will look after it passes through them will be different. So for example, bone is very dense, so it will appear white, and you're going to accumulate that image on the screen until it looks something like this. All right, so here we have, for example, bones. They're absorbing a lot of energy, whilst, for example, the air inside the lungs doesn't absorb any energy, hardly any energy at all. And the screen will collect that and produce the image. Now, when you have scatter, okay, so when you have scattered radiation, that's going to lead to the image quality being worse, because you have all of these random rays that are coming out of the body from the effects that we saw before, such as the photoelectric and the electric such as the photoelectric effect and the Compton scatter. So you're going to have all of these random X-rays that are leaving the patient's body and they're hitting the screen. And so what that's going to do is it's going to reduce the image quality. Now, typically, the reflex response to that is to increase the dose of X-rays that you're hitting the patient with. But that's not really a good solution, because, like, what, are you going to put them inside a nuclear bomb and then take an image of them that way? Like, it's not a very workable solution. And so instead what we do is we use these grids. All right. And so what the grid does is, as you can see here, is that all of these random scattering radiation, all of these randomly scattering rays, they're going to crash into the grid. And so that means that only the rays coming directly from the X-ray tube that manage to pass through the patient will be able to hit the screen. Now the other way is by using an air gap. Because of these scattered rays traveling in all of these random directions, if you move the detector away from the patient, if you put this distance, these scattered rays will be traveling all over the place and they're going to miss the patient. Okay, now here's what we mean when we talk about image quality. The grid, sure. So here we have a metal grid, is what's happening. And so if you look here, you'll notice these. So if you notice here, you'll see these rays that are hitting the part of the grid. They're hitting the walls of this grid. Now what that means is that the grid is going to absorb that energy and it's not going to get to the detector. And so unless the energy is traveling directly from the X-ray tube, passing through the patient and then through the grid, then it will get to the detector. But all of these random rays that are coming off of the patient, because of stuff like the scatter, the photoelectric effect, all of these random rays that come off of the patient, they're not going to hit the detector and they won't affect your image quality. Okay, wonderful, thank you. So here's the first thing, which is spatial resolution. And it's the ability to distinguish two lines that are directly next to each other. Okay, you can think of it like the pixels in an image, right? So here you can see this image is really not clear because there's hardly any pixels going on, right? Whilst this one has a lot more pixels going on in the image. Contrast resolution is the ability to detect different colors, right? Now you can see here, for this one, there's a lot of shades of gray, right? So if there's, for example, here a tiny blood vessel, you can view that because it has a very high contrast resolution. It can produce a lot of different colors of gray. Whilst this one, there's basically only two colors, white and black, and there's nothing in between. And finally, temporal resolution, which we measure in frames per second. Now, temporal resolution is only helpful if we are looking at a video. Okay, so for example, let's say you're filming a patient by X-ray whilst you're making them swallow, such as in a barium swallow, and we measure it. So that's going to require temporal resolution, which is measured in frames per second. Now, I could explain what all of this means, but I personally feel like it's a lot easier to just show you. So here's what we're going to do. Now you can see here in the video that you have all of these different frame rates and all of these different temporal resolutions. All right. Now you'll notice here the 15 frames per second image is a lot more jittery, and it basically feels like it's not even moving, it's just jumping from frame to frame. Where you'll get with the 60 and the 120 frames per second, the movement's a lot smoother. So next we have fluoroscopy. So fluoroscopy is a demonstration of temporal resolution because you need a real-time video where you're going to make the patient swallow barium and you're going to measure how the barium moves as they swallow it. Okay, now for mammography, it's these are a bunch of numbers you have to memorize. I'm sorry, there's no real two ways about it. The things that affect, so because contrast resolution is affected by the voltage, it's affected by the energy of the X-rays. There are things that we do to limit it by limiting kVp for mammography. Again, these are literally just numbers you have to memorize. Like you have to know that the kVp for mammography is 35. And this is what that looks like. So you can see here that there's most likely a mass in this region. So I'm not going to talk much more about it, so we don't spoil for tomorrow. Finally, for this lecture, we're going to talk about radiation dose control. And there are three ways that we can control it. Okay, the first one is by lowering our kVp. Now the key thing is that when it comes to dose, KVP is exponential. All right, so to illustrate this, so we have for every so each time KVP doubles, the amount of dose you're delivering to the patient is going to be times 4. Okay? And if you have 3 times the dose, you're going to get 9 times. If you have 3 times the KVP, you'll get 9 times the dose. And so 4 times the KVP, 16 times the dose. Now, as you can see, it's exponential. All right? So if you want to have your patient get the least dose possible, you're going to want to keep the KVP as low as possible, whilst keeping it high enough that you can actually see something. The other thing is current. Now, as we mentioned before, current tells you how many electrons are hitting the anode. Okay? And so what that means is it's how many rays are coming off of the anode. And so the more electrons, you'll get more rays. But for this one, it's a linear relationship. So 2 times the current means 2 times the dose, while 3 times the current means 3 times the dose. Okay? And finally, we can reduce scatter, or we can reduce the scatter or the air gap, or by creating an air gap, or by using a grid, which is all the methods we mentioned. The main idea behind this is you want to minimize the dose that you need to use. Because again, when you're a radiologist, if you're not getting a good enough image, what you're going to do is you're going to do things that will increase the dose. And we don't want to do that because that will hurt the patient in the long run. Okay, so next we're going to be talking about CTs. Just get straight into it. CTs and X-rays are very similar. The main difference is that where you have X-rays will produce a 2D image, CTs can produce a bunch of 3D sections. So you can look at a 3D image, basically. Right, so it's the same principle. You have this X-ray tube, cathode, anode, electrons travel across, and it releases the X-rays. Again, you're going to have the Heel effect. These are going to be your high energy rays, whilst these will be your low energy rays because they have to pass through all the material. You're going to have your X-ray beam collimation again, where you have to gather all the X-rays into a single spot. And finally, again, you're going to apply the bow tie filter, where you have your source here, and it's going to release all of these rays. And you're going to use a bow tie filter because if you're looking at the patient's chest, you don't want to look at their head, you don't want to look at their abdomen, so no need to send the rays in those directions. And once again, the grid for scattering, in the same principle, it's all the same thing for CTs, up until this point. Okay? So, how do we know for this lump? Heel effect again? Sure. So, here we have, so here on this image, we're going to have this angle, right? So we have this angle basically. For X-ray tubes, it's usually 30 to 60, but that's not an important number. The key thing is that there's 2 parts to the X-ray. Now remember, when you hit the anode with electrons, all of the anode is going to produce X-rays. It's not just this surface. So you're going to get X-rays produced here, you're going to get X-rays produced here, you're going to get X-rays produced here. Okay? So for X-rays produced here, there's very little material that they need to pass through before they leave the anode and go into the patient and then the detector. And because there's less material, these X-rays are going to have a lot more energy left over. As for these X-rays, the ones that are produced here, they're going to need to pass through all of this anode before they leave and then travel to the patient. So that means that these ones are going to have a lot less energy overall. And so that's the Heel effect. The Heel effect is basically that you have this heel shape, and so, yeah, you're losing it. So again, we need to tell all right, sure. So the main idea is for KVP is that when you have a higher KVP, the electrons are going to have more energy. And so when the electrons have more energy, the X-rays will have more energy. Okay? And so when the X-rays have more energy, they're going to pass through the patient more. And so what that means is is that you're going to get a lot more X-rays that will reach the image, and so that can improve, in theory, the image quality. Because at the end of the day, you do need rays that pass through the patient to get something on the slide. Right? Otherwise, it's going to stay as a blank sheet. And so as you increase KPP, you're going to get more X-rays. More X-rays means you're going to get, increase KPP, higher energy X-rays, more X-rays that will hit the image. And so that will produce a higher quality image because the computer will correct for it afterwards. Does that make sense? Okay. So here we have our lump from the lungs, but again, this image doesn't tell us where the lump is. This lump could be deep inside the lungs, or it could be at the chest wall. Sorry, just give me a minute to get a glass. Okay, so here we have this lump. Now we don't know if it's on the chest wall or if it's deep inside the chest. All we know that it's in this general region. And that's why we use CTs, because CTs will give you this sectioned image. And see, now I can tell that it's it's in this area, it's in this specific area. And now you might be asking, okay, now I have a single section. What can I do with that? I don't know if it's in this height or in that height. The thing about CT is you're going to be taking a lot of images at once, and so you can scroll through them and figure out where it is. Okay, so the basic thing is that CTs use the same general principle as X-rays. It's just, for X-rays, it's a single projection that will hit the patient and then reach the detector. Whilst in CTs, you're going to have, whereas for CTs, you're going to have this X-ray tube, and it's going to spin around the patient, and then you're going to have this detector over here, which will also spin around the patient, and what it's going to do is that as it spins, it will constantly take images, it will constantly take snapshots, and afterwards, a computer will compile these snapshot images into a more complex one. Okay, and again, you have the same principles apply with resolution, with spatial resolution being pixels, contrast, temporal. The only difference is now that we have the factor of breathing artifacts. Okay, because the CT scan detector and the X-ray tube is spinning, what that means is that as it's spinning, and until it reaches the new angle, the patient is going to be breathing, right? Because you can't just tell the patient, hey, hold your breath for the next 3 hours, we're going to be taking a bunch of CT images. And so what that means is that as it takes the picture, the patient's going to be breathing. And so each time, the image might look a little bit different because, for example, one time he had his breath in, one time he had his breath out, and so on. So it's the same principle with attenuation, where bone will block most of the light, air is not going to block any light. And again, same principle, spatial resolution, where it's affected by the detector size and obviously your screen pixel size. If you're rich and you have a 4K screen, you're Gucci. Same thing with your X-ray detector. If you get a 4K X-ray detector, your images are going to look a lot better. And the thing about detector size is smaller detector size means a higher resolution. Okay, so here you have the pixels principle. It's like, more pixels, higher resolution. Okay, so for attenuation in CT scan, what we use to talk about attenuation is HU. Now, HU stands for Hounsfeld unit. You don't need to worry too much about the spelling of it. It's the Hounsfeld unit, it's HU. So the key thing is because our bodies are very, like, there's a lot of water in our bodies, so we set water to be 0 Hounsfield units, and then air, which is less dense than water, and so it's going to block less X-rays, is going to have a negative Hounsfield unit, whilst muscle and bone are more dense than water, so they're going to have a positive Hounsfield unit. These are just numbers for you to memorize. And yeah, so muscle, bone, more dense, more attenuation, higher Hounsfield units, air, less dense, less attenuation, lower Hounsfield unit. Again, contrast resolution. So you have, when you have a higher contrast resolution, you're going to get all of these grays that appear. Same concept in CT scans. With contrast, with a higher contrast resolution, you can see more differences with different, like, because more grays are appearing instead of it just being a black and, like, a solid black and white image. Okay, so with this, you have window level and window width. Okay. So the window level is basically what you are looking at, like what you are setting as visible, whilst the window width is the range of what you can look at. This sounds like I just said a whole bunch of garbage, but let's go through it right now, and hopefully it'll make sense. So the first thing is you have your long window. Okay, now when you're looking at your long window, all right, you're basically looking at the lungs. Okay, you want to see the lungs. And so what that means is that all of those gray colors that we were talking about with contrast resolution, we want those to be focused on the lungs. The bone, I don't care about. It can all be white. Air, I don't really care about. That can all be black. But the key thing is that the lung tissue, I want to be able to visualize that as much as possible. So with the long window, I'm going to pour all of my contrast resolution into the range where the lung tissue will start being visible. Okay, now because the lung is mostly air, that's going to be a very low attenuation. It's going to be a very low attenuation, and what that means is that most of the bone and most of the other stuff is going to be completely white, like completely bleached out. But that means that you can see the lung very, very easily. Okay, and the same concept is with the mediastinal window. You want to see the structures in the mediastinum. You don't really care as much about bone, so that can all be bleached out, that can all be white. And you don't really care as much about the air, so that can all be completely blacked out. But when you want to see the grays, all of the gray color, so you can tell the structures apart, you're going to put those pixels into the mediastinal, like into the range of attenuation where the mediastinal tissue is. All right, and so that is the window level. So for the lungs, the window level is going to be centered around the attenuation of the lung tissue. Whereas for the mediastinal window, it's going to be for the structures in the mediastinum. The window range tells you, the window width tells you how much we're going to, like, what's the range that we're going to be looking at. Okay, so a wider range will allow you to spot more structures. But the downside is that you're going to find it more difficult to separate very closely related structures together, like structures that are very closely related together. So for in this case, if you have your lung, you want to see all of the bronchioles. But the issue is because you have all of your bronchioles and you have all of your alveoli, and they're very, very similar looking, right? You need to be able to tell those apart, and you need to be able to separate them from the parenchyma. And so if you increase your range, you're going to find that doing that more difficult. But it also allows you to separate stuff like lung tissue from bone, for example, through increasing your range. Now here you have your liver window, which is where now we're focused on looking at the liver. Okay, so because the liver is a solid organ, because it has its tissues, so our window now for the CT scan is going to be focused for the attenuation range of the tissues of the liver. So stuff like fat, stuff like the parenchyma, the collagen, the parenchyma of the liver, And because of that, you can see all of these small structures in the liver, which are most likely cysts, or it could be the structure of the bile tree, but that's not important. The main thing is that for the liver window, it will focus the image on the liver in terms of color. All right. Similar to how if you like raise the lighting on your phone camera, if you put it too dark, you're not going to be able to see anything because everything will turn black. If you turn it up all the way up, everything's going to look really bleached out, and so you aren't going to be able to see anything then. And so what you want to do is you want to set it based on the lighting of the setting you're in. Windows are the same thing. Now the window that's a little bit different is the bone window, because again, for bone, because bone is a very dense structure generally, that means that it's going to have, that means that if we want to look at the bone, we are going to have to raise our focus of attenuation really, really high, right? Think of it similar to how if you have your phone camera and you point it up at the sky, you're not really going to capture anything. And so you have to raise the brightness on your camera all the way up, and then you might start to get a bit of an image of the stars in the sky. Okay. So now we have our iodinated contrast. This is a little bit of a cheat sheet that doctors can use to help visualize structures more easily. So for example, in the mediastinum, you're going to have this case where there's a bit of, there's something wrong going on with the aorta. Again, no spoilers there. And so what you're going to do is because these two structures, these two tissues, are usually very similar in the body, right? Because it's all just artery. And so what you're going to do is you're going to inject iodine, which has a much higher attenuation, and that's going to help you visualize the difference between these two structures. Now, why is iodine so good? Is because it has this little K edge thing. Now here it tells you how much attenuation is going on across the different X-ray energy levels, and you'll notice that there's a little jump in attenuation as we go into higher energy levels. And this is because the photoelectric effect, again, this is because what's happening is the X-rays are hitting the electrons in the iodine and they're releasing it. And this is the perfect zone for those X-rays to do that. Okay, and so what that means is that beyond this point, with the high energy level rays, you're going to get the tissue, the bone and the tissue in this range. It's going to look a lot brighter than stuff like soft tissue, stuff like blood, fluids, and so on. And here's just another number to memorize, which is the 33 keV, and that is where the K edge is. Okay, and again, we're going to be looking at a radiation dose. So the first one is your FOV, which is how wide your viewing is. So if you're going to add 10 centimeters to your FOV, you're going to have an increase of 10% in the dose. The simplest way to think of it is FOV is like zooming in and then zooming out. Okay, so if you're increasing your FOV by 10 centimeters, right, if you're basically zooming out by 10 centimeters, you're going to get a 10% increase in the dose. The next thing is the kVp, which, like we said, is the voltage across the X-ray tube. And so what that means is that with a higher kVp, you're going to get higher energy electrons, and so higher energy X-rays. And again, this is exponential. And so the relationship is by the kVp, the increase in kVp is squared the increase in dose. So 2 times kVp means 4 times dose, 3 times kVp, 9 times the dose, and so on. Current, again, the relationship is linear because it's just the amount of rays. And finally, we have how much time you're spending in the machine. The more time you spend in the machine, the more dose you're going to be exposed to. And again, this relationship is linear. If you spend twice as much time, you'll get twice as much dose. All right. And now we move on to the radiation protection, which is what we've been talking about for the previous while. Now, because all of these X-rays, they can cause cancer, and they can do a lot of damage to tissue. And for example, they can also cause necrosis. And so what we want to do is we want to lower the amount of dose we're exposing our patients to. Now, I'll get back to this in a second, but there's two different types of effects. Okay, so the first one is your stochastic effect, which it's not dose dependent, it's not exactly dose dependent, but you do get an increasing probability with higher doses. What this means is that if you do 2 X-rays, right, if you do 2 X-ray images, you're not going to get twice as much risk of cancer as if you do 1 X-ray, but there's still a higher probability if you're doing 10 X-rays compared to if you're doing 5. Okay, and so that's your stochastic effect. And the key thing is there's no threshold, right? So there's no point where you're going, okay, if you do 1 more X-ray, you're going to get cancer. Like, there's no threshold like that. And that's why stuff like cancer, which because cancer happens by chance from the mutations, a lot of things that impact cancer are stochastic effects, and one of them is radiation. In fact, and the second type of effect is your deterministic effect, which is dose dependent. There is a threshold to it. And an example of this is the cell necrosis that can happen. And so there's actually a pretty fun documentary, if you want to read about it, which is the most painful death that anyone has ever experienced. What happened is that basically they were exposed to what is basically a nuclear explosion, but for only a few seconds. Okay? And because of that, they survived, but a lot of their tissues died. Now you'll notice that doesn't usually happen when you go to an X-ray machine, right? Because this is dose dependent. There's a certain point where if I'm throwing like 3 tons of X-rays at you, okay, then it's going to actually start causing damage. There is a threshold, and it is dose dependent. So the more past that threshold, the more the damage is going to get. So because of these facts, because of the fact that X-rays can cause cancer and they can cause tissue necrosis, we don't want to expose our patients to radiation unnecessarily. And so we follow a principle called ALORA, which stands for as low as reasonably achievable. For stuff like time, so how much they're being exposed to it, distance, and shielding, so how far away they are and if they're wearing any protection. And there are also other principles that we follow, which is justification, optimization, and dose limits. That's the wrong spelling of dose, but okay. So justification basically means if you're doing an X-ray, there has to be a reason for it. You can't just give your patient X-ray because that's what you're feeling today. There has to be an actual reason. Optimization is stuff like the grid, stuff like the air gap that we talked about before, where basically we're trying to minimize the dose and get the best image possible. And finally, dose limits is what it basically means is don't put your patient in 30 X-rays in one day. All right. So time, again, if you're spending a lot of time near a radiation source, you're going to absorb a lot more radiation. And so that's why, for example, physicians that work with radiation, such as radiologists and stuff like that, they need to have preparation for that activity to protect themselves from the radiation. Distance. Okay, so the way distance works is the further away you are from the source, the less radiation you're exposed to, because a lot more of the radiation is going to be shot out, is going to miss your body, basically. So if I were to draw this very briefly. So here you have your source. Let's say you have your patient. Let's say you have your patient here, and then another patient here. if you're getting, this patient's getting hit by all of these x-rays, whereas for this patient, a lot of those x-rays are going to miss. All right, that's basically the principle for distance. Now, shielding is where we actually make the patient, we actually put stuff to protect the patient from the radiation. So if you've ever taken an x-ray before, they might have had you wear a lead skirt. And so this is to protect some of your abdominal organs from the x-rays. And so because we are trying to protect against radiation, you need something like lead, because it's going to have a high mass number and it's going to be very good at blocking those x-rays. And yeah, so you have your lead aprons, you have your thyroid shields, and you have your eye shields. These are stuff that we use to protect patients and practitioners from the x-rays that we use in practice. This is looking at attenuation, so different stuff are going to be better at blocking x-rays. So for example, air is generally not very good at blocking x-rays. By comparison, stuff like concrete and copper are really, really good at blocking x-rays. And so we prefer, for example, if you're going to have, and so as an example, if you're going to put someone in a room, like if you're going to put someone behind a wall and you want them protected from x-rays, you're going to want a good amount of concrete between them. But as you'll notice is that as the KEV increases, you're going to have more energy in your x-rays, and so these are going to be less effective. Okay, so this is the justification. When you're exposing your patient to medical radiation, the benefit has to outweigh the risks. Pretty straightforward. Okay. Now, optimization is, for example, we can do optimization through the stuff we mentioned, such as the grids and the air gap. The other way you can do is you can control who's going to get exposed. Okay. So as an example, if you're going to request a CT brain, only request, like for example, a CT brain scan if your patient is in an emergency department and they have a very severe headache, which, as you guys probably know already and they're very traumatized from, they probably have a hemorrhagic stroke. They might have a hemorrhagic stroke. And so that's when you're going to want to request a CT. And in that case, you'll only request a CT for the head rather than requesting it for the whole body. And similarly, you aren't going to request a CT for anyone that walks into the ER. Finally, you have dose limits, which is so for dose limits, what we're going to do is we are going to say, hey, beyond this dose, we don't want people exposed to like higher doses than our dose limit. And for this case, there's two groups. There's the public and there's occupationally exposed workers. The public is just the general population, and exposed workers are people that are generally going to be exposed to a lot of radiation. And so we have to put different limits because they are definitely guaranteed to get exposed higher than the public threshold. Now, this is a basic, this is just a principle for how we calculate how much your body is absorbed and how much it's going to be affected by it. You don't really have to worry much about the fancy maths for this. Okay, so it's just, there's a lot of different types of radiation. There's different body parts all respond differently to the radiation. And that's how we look at controlling the dosing. Okay, so ultrasound is next. Okay, so first we're going to look at characteristics of ultrasound waves. So sound, much like most of the things we use for imaging, does travel in waves. All right, and the way these waves will move is you're going to have and so the way these waves will behave is based on stuff like wavelength, which is measured in distance, and it's also based on other stuff such as frequency, which determines like how many vibrations per second, and amplitude, if I can find it. Yeah, and amplitude. And so these are just basic features of the sound wave. They're going to have a wavelength, a frequency, and an amplitude. Okay. So here's your wavelength, which is the distance between two equal points on a wave. So here's the the crest or the highest point. And so the distance between these two is your wavelength, or the distance between the trough and the trough, or like the distance between these 2 points where the wave starts going down. That's your wavelength. Similarly, your frequency just tells you how many vibrations per second. And then you have your amplitude, which is the distance. Okay, so this diagram is also a little bit wrong, but we can make do. So the amplitude tells you how much the distance is from 0. So this here is the amplitude. You can think of it as the height of the wave. All right. And finally, we have velocity. That just tells you how quick the wave travels. Okay. Now sound in air travels at 340 meters a second. Humans can hear a range of 20 to 20,000 hertz, or 20 hertz to 20 kilohertz. And what that means is ultrasound is just above that range. All right. So 20 kilohertz. If you go above 20 kilohertz, then it's ultrasound. This is your amplitude again, which is measured in decibels. And this is the basic principle of your ultrasound. Is you're going to release the sound wave, it's going to hit something over here, and then it will bounce back and get detected. And this here is what that looks like in practice. Here you have your transducer. It releases a wave which bounces back and travels back. Now, similar to how we had attenuation for X-rays, in this case we have acoustic impedance, where what that means is how much the sound wave, like how quickly the sound wave, and how much is it able to travel through the medium. Okay, and it's also determined by stuff like density and stuff like hardness, but you don't really have to worry yourself too much. Okay, now we're looking at a bunch of behaviors of a sound wave within the medium. So the first thing is you can have attenuation. So here, the sound wave travels, and then part of it bounces back, and then part of it continues. Okay, but the key thing is that it continues at less energy, and we're going to see this later. Absorption is just where the further it goes in, the more energy it loses. Now you have reflection, which, as we said, sound wave goes in and bounces back. Next thing is you have scattering. Okay. So next thing is you have scattering, where it's going to hit this object here, and then it's going to bounce out all over the place. You have refraction, which is where it's going to reach a surface. So these two areas are different. So this is area 1, area 2. These are different materials, and so as it travels, it's going to bend. Finally, you have diffraction, which is when sound hits a corner, it will bend around that corner. Attenuation, like we mentioned, is the loss of energy. So here, as the sound travels through a medium, it's going to lose its energy. Now, the principle here is that higher frequency waves higher frequency waves get attenuated more than lower frequency waves. What that means is that if you want to look at something that's deep inside the body, you're going to need to use a lower frequency wavelength. The reason for that is if you're using a higher frequency wavelength, it's going to be very attenuated. It's going to get attenuated quickly and it won't be able to reach. Okay. Now, the next factor is reflection, which, like we said, a wave travels in, bounces off. Now, you can have your echoes across a surface, like in this one, or it can scatter, like we mentioned before. And so this is what reflection looks like. So as you can see here, is the sound wave is hitting this part of the patient, and then it's bouncing off. And what that creates here is it creates this acoustic shadow where there's a lot of darkness. Okay, and that's because all of the sound waves are reflecting off. All right, so this here could be, for example, there's a bone here at the top, and that might be causing that, such as if you're looking at the ribs. Or it could be a change in the surface if, for example, the probe isn't properly aligned, or so on and so forth. Now, similarly here is that there's an object over here, there's a line. I'm going to erase that drawn line so you can see it. But you can see here that there's a line, and you can see that behind it there's another acoustic shadow, an area where there's dark. And you can see that because of this grey line over here, where suddenly everything's becoming brighter. Now, then you have refraction, which is where the sound bends as it travels through different media. So in this case, here we have, for example, air. The sound is going to travel through, and then once it hits the tissue, it's going to bend and travel at a different direction. Okay? And the amount of refraction is affected by the angle of the incidence beam and the density of the tissue. Okay? So let's say, for example, this is air, and this is water. Okay? So as we increase the angle that it's hitting the surface of the water, the new angle is going to be greater. Okay. The other thing is that let's say that this area over here is glass. Now glass is denser than water, and so what that means is that it's going to bend the sound wave. It's going to bend the sound wave more than water. Okay. And so those are the two key things to know. The first one is that the greater the angle, the more the refraction, and the second thing is that this is called the index of refraction. So the greater the index of refraction, the more the bending. Okay. Now, in this case here, you'll notice that there's a bending of the sound wave. Why is mine? So here we have the sound wave is getting bent, and you can see that from this bright line over here. And because of that, what that's causing is it's causing a reflection within the patient's body, and that's causing a mirror image structure to occur. So when we are looking at the ultrasound, this is what the structure of the transducer, which is producing the wave, looks like. And the key principle is that you have this piezoelectric crystal. Now, what a piezoelectric crystal is it's a crystal that when we run an electric current across it, it's going to vibrate. But it will always vibrate with the exact same frequency. Okay? So each time, so it doesn't matter what the current is, this piezoelectric crystal will vibrate with the same frequency, and that allows us to produce a consistent sound when we're looking at the patient's the body structures. So again, as with always, we have our contrast resolution, spatial resolution, and our temporal resolution. Contrast being for color, spatial. Now, for contrast resolution, it's the ability to tell the difference between different structures based on the scale from black to white. I'm not going to touch that again. Spatial resolution is again for distance. The key thing is here is because it's ultrasound and because it's coming from a probe, there are two different types of spatial resolutions. The first one is lateral, which is across the probe, and there's axial. And the difference is that for axial resolution, okay, because it's along the axis of the sound wave, what happens is that the resolution of the beam is determined by the wavelength. So if you have a higher wavelength, or if you have a lower frequency sound wave, then you're going to have a lower axial resolution. All right, so higher frequency sound waves give you more resolution. And if you remember, higher frequency sound waves get attenuated more. And so what that means is if you want to look at surface structures, you use a higher frequency sound wave, because that means you're going to be better equipped to look at them. On the other hand, you have lateral resolution, which is being able to tell apart two structures side by side. And so here you have your axial resolutions. You can see here that when you have a higher frequency, you're able to tell structures apart more easily because it has a higher frequency, whereas a lower frequency is less able to do that. But the positive is that it can travel further, and so you can view lower structures. So you can view structures that are deeper. And here we have examples of the ultrasound. So here we have a hemangioma, where you can see here that it's fluid filled, and so it appears brighter on ultrasound. But the key thing that I want you to focus on here is that for the ultrasound, there's this structure over here. This is a cyst. And now because it's a cyst, it's a fluid filled structure. Right? Now, how do I know this is a cyst and not a hemangioma? Well, the first thing is that this fluid filled structure appears a lot darker than the surroundings on the ultrasound. The second thing is that it has this posterior acoustic enhancement. What that means is that everything past it, everything after it, appears brighter than the surrounding area. Okay? Now, similarly, this is what a gallbladder looks like on ultrasound. The reason you can tell that it's the gallbladder is because the outline is very bright, and because it's right next to the liver. But because the outline is very bright here at the bottom, so you can identify it as the gallbladder. Now, what changes is when you have a gallbladder stone, is you're going to have this structure, this very bright structure here, and then you're going to have a very dark shadow past it. And what's happening in this case is you have all of the sound waves are bouncing off of the stone, and so no sound waves are reaching this area, and so you're going to get a shadow. Similarly here, there's also a stone, and so no sound waves are reaching this area, and that's why it appears so dark. On the other hand, with the posterior acoustic enhancement, sound waves are very, very easily traveling through the cyst, and they're not getting absorbed as much, so more sound waves appear here, and so it appears brighter. Okay, so here's a kidney, right? This is what a kidney looks like. You can tell because you have the cortex here, and then you have the medulla of the kidney. Now this is what it looks like when there's a kidney stone. Again, you'll notice that it's very able to reflect, so you get this dark posterior shadowing. Okay. So here you have your piezoelectric crystal, and it's going to vibrate at a consistent frequency as you send an electric current throughout it. But the key thing is that you can still control the frequency, and there's two ways you can do this. I'm just going to check something. Okay, so So basically, what's happening with the piezoelectric crystal is it's going to vibrate here as you send an electric current throughout it. And it's going to vibrate at a constant frequency, okay? But the key thing is that the frequency can change with the current. And the other thing is that you can have like a difference. So you can have one crystal over here, you can have a different crystal over here to vibrate at a different frequency. Okay. Or, as I said, you can just change the current again. Okay. So yeah, that's a mistake on my part, my bad. The current, as you change the current, the frequency of the vibration will change. Okay. The key thing about the piezoelectric effect is current passes through, it vibrates, because not every object does that. Now again, you have your stones on ultrasound, and then you're going to get posterior shadowing. And so for this case, it's hydronephrosis, which, as you can see here, there's a lot of fluid inside the kidney, and you can tell again by the enhancement, where it appears a lot brighter behind the fluid. And this on CT is just to show you that it is actually hydronephrosis. Okay. Now again, this is a cyst inside the kidney, where you're going to have your enhancement again. And finally, you have a solid renal mass, and the reason you can tell it's a solid renal mass and not a cyst is A, because it's appearing it appears brighter than the surrounding kidney structure, and the second reason is because you don't have the posterior enhancement. Now, this is what a thyroid looks like on your ultrasound. So you're going to have your two thyroid lobes, and then you have the trachea in the middle, and that's why you get this darkness in the middle. Now, this is what a thyroid cyst looks like. Right, so you have your trachea over here, and so here you'd have your thyroid lobe, but you'll notice there's the darkness in the middle. And if I can erase, you're going to get your posterior enhancement. And now, by contrast, you're going to get your trachea over here with your thumb. So by contrast, you're going to get your trachea over here, and then you're going to get your nodule. And so in this case, the nodule's cancerous, and like I said, you can tell that it's not cyst, A, by the darkness, and B, by the lack of enhancement. And so here on ultrasound, you can view the adrenal glands. I can see it's this tiny structure over here that's by the liver and the kidney. Now they're going to be above the kidneys and they're going to have the inverted Y shape. So let me just, so here's the adrenal gland and then the attack. Like this is what it's going to look like. Second. Okay, so here's going to be your adrenal gland with the inverted Y shape. Now this ultrasound is usually done, for example, in children, where they might have adrenal hyperplasia, congenital adrenal hyperplasia. And so you're going to want to view the adrenal gland in that case. So next we have MRI. Can we take a short 5-minute break in the middle? Is that okay? So, the basic principle of MRI runs on the idea that protons have a property called spin. Okay, and basically it's a type of momentum. I'm not going to bother you with the physics details, but the idea is that this spin can interact with magnetic fields. Okay, and the other key thing is that the atoms that are useful for MRIs have an odd number of protons. So in this case, hydrogen, because it's all over our body, because of water, it's very helpful when we're running MRIs because it has an odd number of protons, and so it can have a net spin. Okay, so because if you have an even number, the spins will cancel out. All right, and so the spin of protons can be affected by their surrounding environment. So we mentioned magnetic fields, but it can also be affected by other variables. Okay, and so the contrast inside an MRI is affected by where the protons are and how they're behaving within that environment. Okay, now like we said, these protons have spin, which generates their magnetic field. Okay, and the spin can be influenced by magnetic fields. All right? But usually when inside your body, because you aren't regularly sitting inside an MRI, the spin on your protons is going to be in all sorts of random directions. All right, and so because they're in random directions, the energy is cancelled out, and that's why the human body isn't magnetic. So usually at the start, they are aligned to B0, which is all over the place. All right, where they're going to be spinning, they're aligned to the z-axis, and they're in all sorts of different directions. All right, and then we send our electromagnetic pulse, which is B1. Okay, and that's what that's going to do is it's going to take all of these protons that have spin that's in all sorts of random directions, and then it's going to align them to the magnetic field. So most of them are going to align with the magnetic fields. A few will align against, but that's okay. The key thing is that this provides those nuclei with energy. Okay? So remember that. We're sending a magnetic pulse, which aligns the protons to the magnetic field and provides them with energy. Okay? This is what an MRI looks like structurally. You'll have the patient on the table, and then you're going to have these different magnetic coils around them. And so as you insert them in, they're going to be exposed to all of these, all of the magnet. They're going to be exposed to the magnetic field. Okay? This is just to explain the spin. Again. Okay, no, so one magnetic pulse will align the protons by giving energy. And the key reason is that after you send the pulse, these protons will relax and release that energy, and that's how we view the MRI image. Okay? And so I'm not going to... And so this, in your lecture, wasn't really covered in detail. But the main thing is that there are frequencies that we align with depending on the tissue that we are traveling, that we want to view, that we want to visualize, right? So fat is going to have a different resonant frequency compared to something like water. And so depending on the structure that we're looking at, we're going to be using a different radio frequency. Okay? Now for MRI, it's affected by a thing called inhomogeneity. Okay? So the first thing is that stuff that are diamagnetic, right? And so this is most tissue. This is stuff like water, fat, and so on. Now then we have stuff that are paramagnetic, which is that they respond more, like they respond more powerfully to the magnetic field. Okay, so this is stuff like the gadolinium contrast that we use, and that's why we use it, because it's paramagnetic. And then you have ferromagnetic, which are like very, very responsive to your magnetic field. So stuff like iron. All right, that's why, for example, you don't want any metal objects on you, because they tend to be very ferromagnetic. Okay, so like we said earlier, you're going to release the pulse from the magnetic field, which will align the protons, and then it will relax, and then you're going to send another pulse, which will align them again, and then it will relax again. And so this constant cycle of aligning the protons and then they relax, that's what produces the MRI image. Okay, so this is basically describing that. We're applying the pulse, you magnetize the protons and you align them to the magnetic field, and then they relax again. And when they relax, remember how I said that the pulse applies energy to the protons? As they relax, they'll release that energy. Okay? And this is where we get the concept of T1 and T2 images. Now I'm going to skim over this very briefly, because this was skimmed over very briefly in the lecture. But the key thing is I want you guys to look at this image. Okay, this graph. Now in a T1 weighted image, you're going to send the pulse, and then very quickly you're going to measure after you send the pulse, you're going to very quickly measure the amount of energy that's sent out. And the reason for that is that fat and muscle, those protons are going to relax very quickly, okay, compared to fluid. Now you'll notice here that fluid takes a long time to relax, but in the beginning, it has a lot less energy compared to fat and muscle. And so when you want to visualize stuff like fat and muscle, you're going to use a T1 weighted contrast, because they're going to release all of their energy in that beginning phase, in the T1 phase, right? And so that's what this is going to look like. Okay, so you can see that fluid is going to appear black on this image. Why? Because compared to fat and muscle, fluid has a lot less energy in the beginning phase, in the T1 phase. Could I repeat the graph? Sure. So with this graph, what we're doing here is we're sending the pulse on this line, okay? And then the second line is the point where we start measuring the amount of energy that's released by the protons, okay? And so you'll notice that the gap in this time is very short, right? So we're sending the pulse and then we're immediately measuring the amount of energy that's released by the protons. And the reason is that the protons for fat and muscle relax very quickly, and they release that energy very quickly. And so if you're going to measure it early, right, you're going to get a lot of that released energy that's coming off of the protons in this beginning phase. Whereas in the later phases, you'll notice that fat and muscle don't have any energy at all, and by comparison, fluid now has more energy than fat and muscle. Does that make sense? And this is going to become relevant in your T2 weighted image, where you're going to be able to view your fluid as white compared to fat and muscle. No worries. Okay, so again, T1 weighted image, your fluid is going to appear black here because it has such a low energy, as you can see on the graph. By comparison, your fat and muscle are going to appear as white. Now you'll notice here the bone also appears as white, and the reason is that you have your bone marrow, which contains a lot of fat. Okay, now in the second image, which is on a different section, what's happened here is that they've taken this T1 weighted image and they've basically just removed the fat afterwards. Okay, and the second thing they've done is they've injected a gadolinium contrast, and that makes these blood vessels appear as white. And so now we're going to be looking at your T2 weighted image. Now again, you'll notice with this graph, fat and muscle relax very early on. They relax a lot quicker than fluid. But by comparison, fluid takes a longer time to relax, and so it has more energy for a longer period. And so in a T2 weighted image, you're going to send your pulse, and then you're going to wait a bit, and then you'll start collecting the signal. And what that does is it's going to cause the fluid to light up in the image, and it's going to make it appear white compared to fat and muscle. And again, you can see your fat here appear as grey. Again, you have your bone marrow from your bone. That's going to appear as grey as well. And just like with your T1 weighted image, you can remove the fat attenuation afterwards. Okay? And so this is comparing your T1 versus your T2 based on this principle. So if we look at the brain, we have this is your T1, where fluid appears as black and the fat appears lighter than the fluid because the brain is very heavily fat. And the reason is that because in the early phase, the fat is going to release all of its energy, and so it'll appear a lot brighter. This here, letter C, is your T2 weighted image. And again, because fluids take a lot longer to relax, and so in the later phases, you're going to see the fluid light up a lot more brightly. Number B, you don't really have to worry about it. She mentioned in the lecture that it's not important for this image. Now, for gradient echo sequences, these ones, they behave a little bit differently. So normally what's going to happen is that, we can take the pen. So normally what's going to happen is that let's say you have your magnetic pulse and your detector over here, and so it's going to, and then you have the thing that you're looking at over here. And so what it's going to do is usually with a spin MRI, is it's going to travel 90 degrees this way, and then it will come back and it will travel 90 degrees this way, right, to cover both sides. That, or it will just spin in circles. The key thing is that your gradient echo sequence is going to travel a lot less, right? So if I grab a new color. So with a gradient echo, it's going to travel 30 or 60 degrees this way, and then it will flip and it will travel the other way for 30 to 60 degrees. Okay? Now the thing is that when you're doing things this way, it's a lot faster because you don't have to spin the full direction. The problem with that is that you're going to get you're going to be more affected by field inhomogeneity, and so what that means is you're going to get a less focused image. Just kidding. Okay, so with your gradient echo flip angle, it's going to travel a lot less, and then it will flip and turn in the other direction. All right. And so here's what that looks like. Is, as you can see, you're going to get with your spin echo, you're going to get a much more focused image compared to your gradient echo, compared to your gradient MRI. Okay, now I'm actually not sure which one of these is which, but the key idea is that your spin echo is more focused and it's less affected by inhomogeneity. All right. Now finally we have nuclear medicine. To give a bit of history, you have Henry Becquerel and Marie Curie. They initially discovered radioactivity, and then later it was developed until we started being able to use radionucleotides, and we were able to use it for imaging. Okay. Now, the thing about radioactivity is when you have a nucleus, right? I'm going to draw for a second. There's a bit of a paradox with nuclei. So you have So you have a lot of protons that are condensed in one small area, right? So you have a lot of protons that are condensed in a small area in the nucleus, right? Now, normally these protons are all positively charged, okay? And so they should repel, right? Which is what's happening with the Coulomb's force over here. And so you get the question of, how can a nucleus stay together if you have all of these positive charges that are trying to push each other away? And the answer to that is the strong nuclear force. Okay, and the strong nuclear force will bind the protons and the neutrons together. Okay, so here we have in a hydrogen atom, in a one hydrogen atom, you're going to get only a singular proton. By comparison, a hydrogen 2 atom, which is deuterium, is going to have a proton and a neutron. Now, isotopes is what this is called, right? So we have the same number of protons, but we have a different number of neutrons. Okay, and so these will be bound together by the strong nuclear force. All right, and that's the key idea. And so what happens when we start looking at radioactivity and we start looking at stuff like uranium, stuff like plutonium, is these will have a lot of protons and a lot of neutrons, right? And the thing is that in a lot of cases, when you start putting in a lot of protons, or you start putting in a lot of neutrons, that's going to create a lot of instability, okay? And so what happens is that the unstable nucleus is going to start decaying and it will start releasing different particles. So for example, if we take this hydrogen atom, now hydrogen 1 is very stable because it's just a proton. Deuterium is also very stable, and so is the third one, which is hydrogen 3, where you have a second neutron. Right, so this one here. So this becomes hydrogen 3, because you have a proton and 2 neutrons. The issue becomes is once we start adding a third neutron, is it's going to be very unstable, right? And as a general rule of thumb, nuclei don't like being unstable. And so what it will do is if I draw our third neutron over here, is that this nucleus will start to decay. It will start to lose parts of itself, so it will start releasing some of these neutrons in order to become more stable. Okay? And so here's what we're saying is if you have an isotope, so same number of protons, but more neutrons in this case, if it's unstable, it's going to decay into a different isotope that is stable, and it will also produce particles, which is the stuff that fell off, basically, and it will produce a lot of energy. Okay? And so here we have a chart that's going to describe. Here's a chart which is going to describe what happens as we add more protons and neutrons. Now you can see here that typically things will remain stable as long as the numbers are equal. So if you have 1 proton to 1 neutron, it's pretty stable. But the moment you start stacking on more neutrons, or the moment you start stacking on more protons, that's when problems start to arise and it's going to start decaying. Right, so this is just describing the history of space, I guess, where you have because it's been going on for a very long time, what happened is that most of the unstable nuclei should have already been converted, but there are some things such as lead or thorium or potassium, as well as uranium, but they're going to have very, very long half-lives, and they're going to take basically forever to decay. Okay? And so here's just a graph looking at the different radioisotopes, where you have, for example, for the different number of protons and different number of neutrons. This gray bar is describing to you what is stable. If you start falling off of it, that's where you're going to start to get instability. Okay? So just to give you guys an example here, we have carbon 12 and 14. These are naturally stable, but carbon 14 is unstable, right? And so it will start to decay. And this is actually how we do carbon dating to tell that this dinosaur lived 3 million years ago. And so the other thing is that to perform these actions for nuclear medicine, right? You have what you can do is the thing that you want to do is you want to make the nuclei unstable. Right? You want to break apart these nuclei so they can start releasing radiation, so you can collect that radiation. All right? And so protons, because they're positively charged, they will repel the protons within the nuclei, and so they don't like being inserted. And what that means is that it takes a lot of energy for them to be inserted. Because neutrons don't have a charge, it's a lot easier to insert them into the nucleus. Right? And so here's what that's looking like if you're using like a particle accelerator or a reactor. Because neutrons are very easy to insert, what you're going to be doing is you're going to be throwing neutrons at the nucleus, and that will produce these nuclei that have a lot more neutrons, and then those will eventually decay. By comparison, if you're very rich and you have a particle accelerator, what you can do is you can start throwing protons instead, because you get access to a lot more energy, and then you can produce nuclei that have more protons than neutrons. And this here is looking at the different types of decay that we usually see. So there's three main types that we want to focus on: alpha, beta, and gamma. With an alpha particle, what you'll be releasing is you'll be releasing a helium nucleus. Okay, so you would lose 2 protons and 2 neutrons, right? And so here you can see that happening going on here with radium-226. It will decay into radon-222, losing an alpha particle. All right, and again, this tends to be a very slow process, and as this happens, it's going to release energy. Okay, and so here we have a beta decay. What's going to happen is you have cobalt, which has 27 protons and 33 neutrons, while you have, and what it's going to do is it's going to decay into nickel. And so what it will do is it will gain a proton and it will lose a neutron. And the way that works is that one way to think of a proton is, so this is a proton and this is a neutron. Right, so one way to think of a neutron is that it's, what is that? So one way to think of a neutron is that it's a proton with a neutron attached. And that's why it doesn't have a charge. Okay, but the thing is that it can then decay, releasing this electron, and that will be your beta decay. Okay, it also releases an antineutrino, but you really don't have to worry about what an antineutrino is. You really don't have to worry. Okay, so the final type is a gamma decay. All right, and so the key thing about gamma decay is all that's happening is it's releasing gamma rays, which basically the way you think of it is imagine X-rays. Now give them Russian steroids. That's what a gamma ray is. Okay, and so all that's happening is you have this high energy nucleus, and then it's going to shift into a lower energy nucleus by releasing gamma rays. And this is showing you radioactive decay. So decay happens on a half-life basis. All right? And so it doesn't happen at a constant rate. And so let's say I have a kilogram of uranium, right? The half-life time is constant. So let's say we have a kilogram of uranium, and I actually don't know what the half-life of uranium is. So let's make this interesting. Half-life of uranium 235. So uranium 235 has a half-life of 700 million years, which is great. So let's say I have 1 kilogram of uranium, and I give it to one of you guys, and then I go away, and then I come back 700 million years later. What's going to happen to that kilogram of uranium is it's going to have become half a kilogram. All right? And this happens on a constant basis. So every 700 million years, uranium-235 will lose half of its weight. So if it was 2 kilograms, it will become 1 every half-life. If it was 1 kilogram, then it will become half the next half-life, and so on. So here you can see that being demonstrated. You have your full kilogram over here, and then after a half-life, let me just flip into a laser pointer. So you have your full kilogram over here. After 1 half-life, it becomes half a kilogram. After a second half-life, it becomes a quarter of a kilogram, and then an eighth, and then a 16th, and so on. All right? And that's all from me today. Thank you guys so much. Do you have any questions?